Well, I'm going to make this video to help you begin to learn how to draw force diagrams, or what's commonly called free body diagrams. These are really critical for doing what we call Newton's law problems, or sometimes called dynamics problems. And the funny thing is, this is probably the easiest part, and yet the part that students talk themselves into mistakes all the time. So I'm going to try to, in this video, describe the kinds of mistakes people make and how to avoid it. And then I'll demonstrate how we do these different kinds of diagrams. So I want to start by listing the common kinds of forces that are drawn on free body diagrams. And a force is just a push or a pull, and we categorize these forces and name them based on what causes the push or the pull. So probably the one common force that you'll find on almost every diagram that you draw will be a gravity force. And the only time you wouldn't have this is if you're in the far reaches of space, and those are just not diagrams that you're going to typically draw. So we call it the weight. I like to call the gravity force the weight. Now, that is not universal. There are some physics instructors and textbooks that refer to the weight differently, but I'm going to refer to it as the weight. And you can actually calculate that. I'm not going to go into the numerical part now. And then you'll often have objects sitting on surfaces. If you have a surface, you always have a normal force. This is what presses the surfaces against each other. So if you have something sitting on the road or on the floor, then they are kind of squishing each other. Your tires get squished by the road, and the tires try to squish the road. Or maybe a book is sitting on a desk, and the desk and the book are trying to squish against each other. That squish force is called the normal force. And it's always perpendicular to the surfaces. So on flat desks that are horizontal, then the normal force would be vertical on each object. You can also have friction. And you don't always have friction, but if you have a surface, you can have friction. And that's if the surfaces are sliding or have a tendency to want to slide. I say it has a tendency to slide. So if your car is sitting on a hill, it has a tendency to want to slide down the hill. Friction is opposing that tendency. Okay, now what's confusing about this is students often want to draw friction opposite the motion, but it's actually opposite the tendency for surfaces to slide across each other. And I'll get into what the difference between those will be commonly. Other forces we'll have maybe tension forces. This is how we categorize forces due to things like strings and ropes, cables, and the like. You can also just call it the force of the string or the force of the rope, but it's commonly called tension. I went through my entire Physics 1 experience without realizing that the word tension was another word for force. That's a little embarrassing now, but it's the truth. You can also have springs exerting forces. And because there's a special equation for how much force a spring will exert, we actually categorize it in that way. That way you'll know, oh, I should look for the equation, and it can actually calculate what this is. So I think it's pretty self-explanatory what a spring is. Now, a spring can either push or pull. If a spring is stretched out, it's going to want to pull back. But if it's squished together, if it's one of the squishable types, then it will try to expand and push away. And most of the other forces I kind of categorize generically as applied forces. But always make sure you can say applied by what, and use that as your label. So it might be something like if you've got a rocket being pushed by igniting fuel, then it's actually the fuel that's pushing on the rocket. Or maybe somebody named Bobby just kicked his calculator across the room. So Bobby would be exerting that force. If you can't name an actual thing, a noun, that is pushing or pulling on your object, then it's probably not a force. So for example, if you say, you wouldn't say the force of the motion, because motion is not a thing that can push. You would not say the force of momentum or the force of inertia. None of those things are real objects that can push or pull, so don't name those as forces. So let's look at a few examples now. And you might not be able to read the text, but I'll read it here for you. So imagine we have a car on a very slippery, icy road. It's sliding headfirst into a snowbank where it gently comes to rest with no one injured. So we're going to draw the forces here. You don't need to be an artist to draw forces. I mean, that can be your car. It can be very simple. So I like to have my objects moving rightward. It's just a habit of mine. And I might put little motion tails on just so that I can tell that it's moving rightward. But you can do yours leftward and everything's just going to look reversed. So what do we have here? Well, certainly we have gravity. And so we would draw an arrow with its tail right on the object. Right in the middle of the object is where you put the tail. And then you draw the arrow showing which way the force is acting. And then you put a little F for force, and then you name it or categorize it using those same categories that I just described. In this case, gravity is pulling down, so I'll call it the subscript gravity. Don't write the whole word. A lot of times we'll just write G, but I'm going to put gravity, or shortened as grav. Now, because we're on a road, then that's a surface. So we're going to have a normal force perpendicular to the surfaces in contact. So for the car, it's going to be pushed up by the road. That's what we call the normal force, often abbreviated with just an N. I like to actually write out norm because N is sometimes confused with the idea of a net force, which is not one of the forces we will ever draw on a diagram. I'll explain that in a different video. Notice it says very slippery. That implies that it's so icy that we will not include friction as a significant force. If we did, we would have to know, are the tires, are they locked so that it's sliding? If it was sliding, then we would have friction opposing that sliding and it would be leftward, but we're not going to include that here. Now it is coming to rest headfirst in a snowbank. That must mean the snowbank is in contact with it and is exerting a force. So the snowbank must be over here on the right, and so I would call this is one of those generic forces, and I'll just write the force of the snowbank. If you can't name what it is exerting the force, then don't include it in there. And that would be all that we would have on that one. How about number 5? A compressed spring is pushing a block across a rough horizontal table. The word rough, we'll see, is important here. And we see the word spring. That's kind of a giveaway. So I would draw the block. I don't need to draw all of the other stuff, but I just need to account for the forces. So again, we have the downward force of gravity. And we have surfaces here, and they would be pushing against each other. So this would be the table. That's a normal force. You don't have to write table, although a lot of teachers like you to write what it is exerting the normal force. That way you keep yourself from making up forces that don't really exist. Some people write normal forces on, airplanes flying through the air when clearly there's no surface that it's sitting on. And it says a compressed spring is pushing it. So again, I tend to have my motion rightward. I think that's because that's the direction that I read. And so if we had the spring maybe over here, I don't want to draw too much stuff, but it's being pushed this way if that spring is compressed. So I'll say this is the force of the spring. That can also be referred to as an elastic force in some textbooks and some teachers. And a rough horizontal table, that means there would be some friction from the sliding. That sliding friction always opposes the actual sliding motion. So because I have it sliding rightward across the table, then friction would act leftward, and I'll just abbreviate that FRICT. So we have 4 different forces here, each in the 4 left, right, up, down directions. I'm going to skip to this one here. So if we have block A connected with a rope to block B, then what forces do we have on A? I'm going to show you one of the common mistakes that we see on this. So let's look at what's pulling on A. In fact, I think I'm just going to draw it here to save myself a little bit of trouble. So we have what in contact? Of course, we don't need contact to have gravity. I'm going to start abbreviating that just FG now that we've seen it a few times. We have it sitting on a surface, and so that's a normal force that would go perpendicular to that surface. That's the normal force. It says frictionless table, so that means I don't need to include any sliding friction. And we have what in contact with it? We have this rope, and that's that category that I call tension. I'll use T for that. Now here's the mistake people make on this. They say, well, that tension is caused by the weight of B, and they're going to call it the weight or the gravity from B, and that is not correct. You only write forces on objects when there's things in contact with them. B is not directly in contact with A, so we label it not as B, but with the rope that is actually touching it. So always look for things touching. On this last one, a rocket launched at a 30-degree angle. Air resistance is not negligible. Well, of course, with a rocket moving as fast as it is, it has to be important. So I actually might draw something that looks like a rocket here. Doesn't need to be anything real fancy. Going at a 30-degree angle. So we would have what? Of course, we have gravity. Yes, even flying rockets have gravity exerting forces on them. We do not have a normal force because it's not sitting on a surface. It says is launched. I'm going to assume it's being launched right now. And so the fuel coming out of here, as it's being pushed by the rocket, exerts a force back on the rocket in the direction that it's moving. So I will call this the force of the fuel. Often you'll hear that referred to as a thrusting force. One of the important forces in aerodynamics is the thrust force. But I'll just call it fuel because I like to name the thing that's in contact. Thrust is not a real thing in contact, and so that keeps you from wanting to name things that don't exist. Air resistance is important. Air resistance, we often call it drag, is always opposite the motion. It's a little bit like friction, but it does work a little bit differently. So we're going to have a force this way, and I'll just write air. Again, we could call that drag just as easily. So there's three forces on that, okay? No friction because there's no surfaces, no normal force, and nothing else that I can see in contact with it. So I'm going to do one more here. And this is this last one. You slammed on your car brakes while going down a hill and are skidding to a halt. So I'm going to draw a little diagram. Just put a hill on there. I'm going to draw my car. Again, my very crude drawings. You don't need to be an artist to do a good physics. So what do we have here? Of course we have gravity, and I wanted to show you this one because people sometimes start changing the direction of gravity. Gravity is always straight down towards the center of the earth, even when you're on a hill. So that will not change direction. But what will change direction is the normal force, because it's always perpendicular to the two surfaces in contact. That would be the wheels and the road. So we would draw a force in that direction, angled a little bit, and that's what we call the normal force. Now we're slamming on your car brakes. That means your car is probably skidding, and that skidding is being caused by the friction opposing the sliding of the tires across the road. And now to draw anything else, you would have to name something in contact. People tend to want to draw forces down the hill because the car is moving down the hill. And my question back to them would be, well, can you name the thing that's actually exerting the force down the hill? You have to name something touching the car. I've already named the road by putting normal and friction in here. I've named the Earth's gravity, which is always in contact with everything. And I don't see anything else touching. So I cannot name a thrusting force or a tension or spring or any other applied force. And so that is the end of the forces that are exerted on this particular car. So I think I'm going to stop here. It gives you a flavor for the kinds of things that can work right and work wrong. And you'll be doing these in almost all the diagrams that you draw for these kinds of problems. So I'll let you have at it. And if you need more help, you just find some help from me or another resource. Good luck.